Today we are looking at an application of stoichiometry that we've already talked about, and now we're just going to practice doing the math to figure out what is the limiting reactant and the percent yield for a given reaction. And so the application for this would be if you're going into a lab and you know you have a certain amount of grams of the different reactants that you're going to mix together, and you want to know how much product you should expect to make at the end of the reaction. And so we can do these calculations to tell us theoretically how much we should make. And so that's called the theoretical yield, when we do our calculations and figure out, based on the amount of reactants given, how much product we will be able to make. And most of the time we're going to run out of one ingredient or one reactant first, and we call that the limiting reactant, and the rest are going to be in excess. So we'll start there, and then we will add on percent yield afterward. But remember to review, percent yield is taking the amount that you actually produce in lab, because our calculations are like perfect world example, but when you actually do the experiment, sometimes you may lose some mass, or your sample might be contaminated, hopefully not, but either way, you might not react fully the amount that your calculations will show you, and that's where we use this kind of error analysis called percent yield to compare actual versus theoretical in a percentage. So let's try this number one out, doing our stoichiometry problem. So whenever you're trying to find the theoretical yield, you'll do two problems, one for each of the reactants. So you'll do two conversions. I just underlined the two givens, and then each of those two problems we are going to find the same thing. So it looks like we're finding grams in NaCl. You should be finding a product and given the two reactants, and we are, as we see in this reaction, reactants. Copper 2 chloride, sodium nitrate, and then our product we're trying to find is salt. So let's start by balancing our equation, because we will need that when we do our mole ratios. So it looks like we have 2 nitrates on the product side, so I'm going to put a 2 in front of sodium nitrate to balance that guy out. And now our sodium is 2, so we'll put a 2 here, and that also takes care of the chlorine. So our coefficients are 1, 2, 1, 2. Now we are ready to start our calculation. So our givens, just like I said before, are the amounts of our reactants. In both of these problems, we are finding how many grams of salt. So we're just going to start our two problems here. Same way. Okay, then we're going to do two different conversion problems. So let's start with the top here. Because we're working with grams, we're going to need molar mass to convert into moles. And then our next step will be to use a mole ratio so we can change the compound. And then we'll need molar mass again to find grams of salt. There's kind of our map of what we're going to do. Molar mass of copper chloride, mole ratio, molar mass of sodium chloride. So before we start our calculation, let's just get the molar mass out of the way. Grab a periodic table and start adding these up. So for copper 2 chloride, I get 134.45. So we'll need that. And then for sodium chloride, we're going to get 58.44. Okay. So that's for our first conversion here. Let's put them where they need to go. So we need a molar mass of copper chloride, since that's our given value. Or I guess our given compound, to moles. Okay, so there's our molar mass. Now we are ready to change the compound because we are in moles. We can't do that when we're in grams because that is not taking into account the ratios correctly given by the coefficients. That must be in moles. So our mole ratio, copper to chloride, will be represented with a 1 because of its coefficient here. And our find is NaCl, that is represented with a 2 here. So again, the mole ratio step, we use coefficients. And now we're ready for our last step, using that molar mass of salt, which we calculated to be 58.44 grams. Plug and chug it into your calculator, and rounding we get 13.0 grams of salt. Now we'll just round it for 3 significant figures because that's what we have in the given. So there's our first problem, and what that information is telling us is that we have 13 grams of salt that we can produce from 15 grams of our first reactant, copper 2 chloride, as long as we have enough of the other reactant. So we're going to go ahead and check that one too and see, do we have more or less that will be produced of NaNO3? And because this is also in grams, let's go ahead and do its molar mass. We will need that. Remember, grams tell us we're going to need molar mass. So again, grab your periodic table and calculator and start adding these up. And I got 85 right on the dot. Okay. Now we're ready again to start our process. We're going to do the molar mass of sodium nitrate this time, then a mole ratio to change the compound, and then finish with that same salt molar mass since we're finding the same product. All right, 85 we said is the mass of sodium nitrate. And that's in 1 mole. Okay, so there's our first step. Now we're ready to do mole ratio. So let's take a look at these coefficients involved. We've got a 2 for sodium nitrate, and we've got a 2 for salt. Mole ratio done. And then lastly, molar mass, same as before for salt. Pop it in your calculator, and this one we get 13.8 grams of salt from 20 grams of sodium nitrate. So what this problem is telling us is that we are going to be able to make 13 grams from our first reactant and 13.8 grams from our second reactant. But overall, we're only going to be able to make as much as kind of that least available, or our limiting factor, right? So we're going to choose the smaller answer. Whenever we do a theoretical yield, you'll do multiple problems, one for each reactant, and you'll always choose the smaller number. So our theoretical yield will be, in this case, 13.0, since that's smaller than the other calculation. Okay, so there's our theoretical yield. And we're going to place that in this blank here. Overall, 13 grams of salt will theoretically be produced. Again, that's like in a perfect world, according to our calculations, that's how much we should be able to make. And that will take up all of this copper 2 chloride available to make it. So this is our limiting reactant. Whenever you decide which one's your theoretical yield, your smaller answer, just kind of look back to where you're given, what it started from. That's going to be the factor that limits you because it's going to run out and be used completely in the reaction. To answer our next question then, which is the limiting reactant, that would be copper 2 chloride. Which is excess? Well, that would be the only other option, sodium nitrate. And that's because our answer was larger. It could make more than what we're going to actually make. So we're going to have excess. Our last part here is asking about percent yield. And if we look back up at the box, we've got actual over theoretical times 100. So this number here, 11.3, it says that it was produced in lab. This is your actual value. And we're going to compare that, kind of that error analysis we've talked about, the actual amount we got in lab compared to what we should have been able to get in a perfect world, 13 grams, and find out what that percent yield is. So we'll take our actual divided by the theoretical times 100, and you'll get 86.9% yield. On our percentages, I'm not going to worry too much on your rounding, so if you do ones place or tens place, either one is fine as long as it is in the same ballpark. It will be counted correct. So this is an 86.9% yield for our value here. Now, if you did have a number over 100, that is possible. I don't think I actually have any examples like that, but just for you to know in future reference, possibly the sample might have been wet. That would be extra mass from water, or contaminated with something else. So 100%, above 100% yield is possible if you were ever to get that. That's just error of extra mass rather than error of not enough reacted. Okay, so there's the process, the whole Stoich process of figuring out how much you can make and then doing an error analysis after finding out what you actually made in lab in a reaction. You'll do 2 conversion problems, pick the smaller one, that's the theoretical yield, determine which reactant produces that much, that's your limiting, and then the other one, or if you have more than one other reactant, those are excess. To find your percent yield, you'll take the actual and compare it with that theoretical to find a percentage. You have a couple more problems on this page that go through the same process with different reactions. So you'll need a balance, and then you'll do the problems, pick your smaller answer, that's your theoretical yield. Then the same idea, limiting reactant, excess reactant, and percent yield. Exact same process, just with different numbers and reaction. And then number 3 also. Number 3, the only thing I want to clarify here is that of our 2 reactants, we have aluminum and oxygen, it tells you that you have excess oxygen. So when you go to write out your givens, you can just write excess because it doesn't tell you how much. But if this is excess, if you go back to the example we just did, the one that was excess, we did not use that value at all. We just used it to compare which one was smaller. So what this is telling us is this is going to be the one that's larger because of that word excess. So you do not actually need to do that problem. Excess tells you they did the work for you and found that one would have a larger answer. So really all you'll have to do is solve for the amount produced from the aluminum, and that will be your theoretical yield.